All right, again, let's talk about Chapter 12 and some tricky concepts relative to the respiratory system. First of all, let's talk about how air moves in and out of the lungs. That's a process that's known as ventilation, and the process behind that is sometimes referred to as mechanics or pulmonary mechanics because that literally means how it works as a machine. To get air to flow in and out of any space, in and out of the lungs, requires a pressure difference. So to get air to move into the lungs during inspiration, there must be a difference in pressure inside our lungs relative to the atmosphere. And to get air to move out of our lungs during expiration, there also has to be a pressure difference from inside of our lungs to the atmosphere. We know that fluids, like air, always move from an area of high pressure to low pressure. Thus, during inspiration, we must create an environment inside our lungs with a lower pressure relative to the atmosphere. Atmosphere being higher, create a lower pressure in the lungs will cause air to flow in. Similarly, during expiration, we need to create an environment inside our lungs in the alveoli that's greater than atmospheric pressure. This will cause air to move from the area of high in the lungs to low pressure, the atmosphere. So how is this achieved? It's a real simple schematic representation of the lungs. This inner area here is meant to represent the entire volume of the alveoli. That's the diaphragm, the rib cage or chest wall, forming the thorax. And then this space here, that I've over-exaggerated, is that intrapleural space, that very small water-filled space between lung tissue and the chest wall or the diaphragm, the intrapleural space. Now this very small water-filled space is essential to creating pressure differences within the alveoli. Let's first consider when we're not breathing and our glottis is open to the atmosphere. The pressure within the alveoli would be the same as the atmospheric pressure. We can put whatever number we want to this. Let's call atmospheric pressure 0, just for reference. It's not 0, it's 760 millimeters of mercury, but it's a reference, so we're going to call it 0. Now, if we're not breathing and our glottis is open to the atmosphere, the pressure within the alveoli is the same, or 0. Now, the space that I referred to before is the intrapleural space, this fluid-filled space here, is sealed off and has a pressure that's less than atmospheric at all times. When we're not breathing, this space, intrapleural space, is on the order of 2 or 3 millimeters of mercury less than atmospheric. Let's call it 2. And I'm going to write it as -2 to indicate that it's 2 millimeters of mercury less than atmospheric. All right. What happens during inspiration? During inspiration, the diaphragm contracts and moves down. The intercostal muscles contract, and the rib cage expands and moves up and out. And this increases the entire volume of the thorax, the chest cavity. Because of the presence of this fluid-filled space, the lung tissue gets pulled along with the chest cavity as it expands. And in fact, this pressure inside the intrapleural space will become even more negative as the chest expands and grows larger. So let's just write -4. This, again, will pull the lung tissue along with the chest, along with the thoracic cavity, increasing the volume in those alveoli. And as the volume in the alveoli increases, the pressure in those alveoli falls. That's Boyle's law. And it falls to be about 1 millimeter mercury less than atmospheric, just a little bit less than atmospheric. And that's all that's needed, because now a pressure difference has been created. with the pressure inside the alveoli less, there we are, than the pressure of the atmosphere. Air will flow into the lungs in this case. How about expiration? Well, with expiration, the muscles relax, the intercostal muscles and the diaphragm. Now, the thoracic volume is reduced, the alveolar volume is reduced, pressure goes up in those alveoli. The intrapleural pressure goes back to its starting point, still less than atmospheric. But because of this reduction in alveolar volume, alveolar pressure has gone up, just barely exceeding atmospheric pressure. And that's all that's needed. Once it's larger than atmospheric pressure, air will flow out of the lungs back to the atmosphere. We have to create pressure differences in our lungs relative to the atmosphere for air to move in and air to move back out. All right, that's mechanics. Let's move on to talk about gas transport, shall we? First, let's talk about transport of oxygen. About 99% of oxygen is bound to hemoglobin. This simple diagram is meant to illustrate oxygen coming into the alveoli and blood flowing through the pulmonary or lung capillaries. The oxygen comes in with the air, and the air moves under pressure into the alveoli. Once it's into the alveoli, the diffusion of oxygen across cell membranes from the alveoli into the bloodstream does not require pressure. It's diffusive. It does require a concentration difference. And this concentration difference is the partial pressure of oxygen. It's a gas in the presence of other gases. So it has a pressure, but only a partial pressure of the total of all the gases. So we can think of this partial pressure as effectively a concentration of oxygen. To get diffusion of oxygen to occur from the alveoli into the bloodstream, there must be a higher partial pressure in the alveoli than in the bloodstream. Just like there has to be a higher concentration difference on one side of a membrane relative to the other for diffusion to occur across that membrane. The PO2 in the alveoli is about 100 millimeters of mercury. Blood comes into the lungs with a PO2 of about 40. That's the partial pressure difference that allows for diffusion of oxygen across cell membranes and into the bloodstream. Blood leaves the lungs on the way to the left heart, having equilibrated with the partial pressure of oxygen in the alveoli. That is, the arterial partial pressure of oxygen is also 100. Where does it go? To the left heart, pumped out of the left heart to the arteries, the arterioles, and finally down to the capillaries, the exchange sites, the exchange vessels. At the capillaries, blood comes in with a partial pressure of 100 millimeters of mercury. Now, these capillaries are in close approximation of metabolically active cells, living cells. And so the partial pressure surrounding these cells is lower than the blood that comes into these systemic capillaries. The cells are continuously using the oxygen in metabolism. The cells have a PO2, a partial pressure, of approximately 40 millimeters of mercury. This is very fortunate because this sets up a situation where diffusion can now occur from the capillaries to the metabolically active cells. Blood leaves the capillaries, enters the venous circulation, having equilibrated with the partial pressure in the area about the cells. That is, blood leaves the capillaries, enters the systemic veins, going back to the right heart with a partial pressure of approximately 40. And this, of course, is the partial pressure of oxygen in the blood that then gets pumped back through the lungs. All right, 99% of the oxygen is transported in the bloodstream bound to hemoglobin. So let's look at the partial pressure hemoglobin relationship. This is just like the figure in the book. On the x-axis we have partial pressure of oxygen, and on the y-axis we have percent saturation, or the number of binding sites in hemoglobin that are occupied holding oxygen, saturated. At the highest PO2, we'd expect nearly all the binding sites for oxygen and hemoglobin to be occupied. That is, we'd expect nearly 100% saturation. Our highest PO2 is in the alveoli and the blood leaving the lungs, pulmonary veins, going back to the left side of the heart. That PO2, as you recall, is about 100 millimeters of mercury. At that partial pressure, that concentration of oxygen, hemoglobin can hold about 99%. 99% of the hemoglobin binding sites are occupied. 99% saturation occurs. So just shy of 100% saturation there. Now, as blood flows out of the left heart to the arteries, arterioles, down to the capillaries, finally at the capillaries, the blood experiences a PO2 in that environment of about 40 millimeters of mercury. At that partial pressure, 99% of the hemoglobin can no longer be saturated. There's not enough oxygen partial pressure to assure 99% of the hemoglobin is bound to oxygen. So the oxygen comes off or is released from the hemoglobin. Thankfully, it does occur because the cells require that oxygen. So the oxygen is released at this lower partial pressure. The cells are continuously consuming the oxygen. At a PO2 of about 40, at the metabolically active cells, blood has about a 72% hemoglobin saturation. Curve looks like that. That is to say 72% of the hemoglobin binding sites still are holding oxygen as the blood goes through those systemic capillaries, enters the veins, and goes back to the left heart. You may think, well, you've gone from 99% to 72%. Seems like a waste. But this allows for a big range or much more oxygen that can be released in times of work or exercise when the cells have an increased requirement for oxygen. If we complete that curve, it'll look something like that. But the 100 to 40 represents arterial PO2, capillary PO2, 99% saturation down to about 72% saturation, at least under resting conditions. All right, 99% of our oxygen is carried this way, bound to hemoglobin. That tiny 1% of oxygen travels into plasma, dissolved as a gas. And here's a remarkable fact. That tiny 1% is what actually gives the partial pressure of 100 in the bloodstream. Okay, let's turn our attention to carbon dioxide transport. Carbon dioxide, a product of metabolically active cells, is transported in the bloodstream in 3 different ways. First, it can be dissolved as a gas, not very well, it's not very soluble, just like oxygen. Second, it can bind to hemoglobin. Interesting fact, actually to a different site than the oxygen binding site. And lastly, and most importantly perhaps, the vast majority, or 60% of carbon dioxide is actually converted by red blood cells to bicarbonate ion, a highly soluble, easy to dissolve ion. 60% of carbon dioxide is transported in a chemically converted form, in an ionic form. This happens again in the red blood cells. There's a red blood cell. It's in a capillary really close to this metabolically active cell. This metabolically active cell has a PCO2 of about 46. So as blood leaves these systemic capillaries on the way back to the right heart, the PCO2 will be 46 or so, partial pressure carbon dioxide. Now, 60% of the carbon dioxide gets converted by this red blood cell to bicarbonate ion. The carbon dioxide interacts with water in the red blood cell in the presence of an enzyme, carbonic anhydrase, abbreviated CA, to promote the chemical formation of two ions, the bicarbonate ion, HCO3-, and the hydrogen ion, proton, H+. That hydrogen ion is quickly buffered by proteins, sometimes hemoglobin itself. And the bicarbonate ion, highly soluble, can leave the red blood cell into the plasma and travel back to the lungs this way in the ionic form. So away it goes, into the systemic veins, back to the right heart, pumped into the lungs. Now let's imagine we follow the plasma and this red blood cell as we enter a pulmonary capillary. There's our alveoli, and there's our red blood cell. And when our blood enters the pulmonary capillaries, carrying a PCO2, partial pressure carbon dioxide of 46, it encounters the alveoli with a PCO2 of 40. This is the carbon dioxide partial pressure difference that allows for diffusion of carbon dioxide from the plasma into the alveoli. So it's diffusive movement of carbon dioxide out of the blood into the alveoli. 60% of the carbon dioxide is arriving to the lungs in the bicarbonate form in the ion. It needs to be converted back to carbon dioxide, to gas, to allow for diffusion across these membranes. As carbon dioxide starts diffusing out of the plasma, the reverse reaction occurs in red blood cells. The bicarbonate moves into the red blood cell, combines with protons, in the presence of the same enzyme, carbonic anhydrase, now forming water and the poorly soluble gas CO2. That carbon dioxide, now a poorly soluble gas, released by the red blood cell, diffuses across membranes into the alveoli to be expired. So the reverse reaction happens in the lungs. And importantly, again, 60% of the carbon dioxide is transported this way in a converted ion bicarbonate form to be reconverted back to carbon dioxide in the lungs. That's kind of tricky. All right, lastly, let's talk about chemoreceptors and their influence on respiratory control centers. Chemoreceptors are specialized neurons that respond to changes in chemical composition. The chemoreceptors we're talking about here are those neurons that can respond to gases such as oxygen and carbon dioxide. And they're found in blood vessels or in the brain. The chemoreceptors that are found in the blood vessels are referred to as the peripheral chemoreceptors. The chemoreceptors that are found in the brain are the central chemoreceptors. Now, it's kind of remarkable that the peripheral chemoreceptors under normal conditions really play little role in regulating the respiratory rate. The central chemoreceptors in the brainstem region are essential in dictating the rate of respiration under normal conditions. So let's look at how those central chemoreceptors are influenced. So the central chemoreceptors in the brainstem are influenced by the amount of carbon dioxide that's in the bloodstream. And that's going to vary by the metabolic activity of cells. As carbon dioxide levels go up, the amount of carbon dioxide that diffuses into the extracellular fluid around the brainstem increases. This carbon dioxide in the brainstem is converted to bicarbonate ion and proton by the same enzyme that we just saw in red blood cells. This time the enzyme is present in the brainstem. It's carbonic anhydrase. Remember that carbonic anhydrase catalyzed the reaction of CO2 and water to form bicarbonate ion and the proton. Here in the brainstem, that proton directly stimulates the central chemoreceptors. But importantly, the concentration of those protons is proportional to the amount of CO2 that's in the bloodstream. So ultimately, it's the carbon dioxide in the bloodstream that allows for creation of those protons that then stimulates the central chemoreceptors. Those central chemoreceptors then turn around and stimulate the respiratory control centers in the medulla. And as the CO2 in the bloodstream goes up, so does production of protons right adjacent to the central chemoreceptors, and thus an increase in the activity of respiration as the respiratory control center is stimulated. Meaning, minute to minute, breath to breath, the primary driving factor for respiration rate is the increase in CO2 in your bloodstream. As you hold your breath, and give it a try at the end of this video, you hold your breath. The reason you've got to stop and take a breath finally is because of a buildup of carbon dioxide in your bloodstream, and thus an increase in protons in the extracellular fluid around the central chemoreceptors. There's a common misconception that we breathe when our oxygen levels reach some low value. In fact, we breathe, we're stimulated to inspire, when our carbon dioxide levels reach some critically high value. That's our last tricky concept for this chapter.